Hello everyone, welcome to the course on Introduction to Multi-Agent Systems. Today is the second lecture on Introduction to Graph Theory, where we'll talk about a bit more properties associated with the walks in graphs. So again, before we begin, let's start with a practical example which we have already looked in the previous lecture. So the bridges of Königsberg. Now as we already know that in this problem, we have the city of Königsberg, whose image is as shown here. Now the Pregel River flows through the city in such a manner that it divides the city into four parts. There are four land masses denoted as A, B, C and D, and there are 7 bridges which connect all of the land masses with each other. So now the question that we were trying to address was, or which was rather posed to Euler, was this: is it possible to do a round trip through the city by traversing each of the bridges exactly once? So we already know that the answer to this question is no, but it actually leads to an interesting point regarding the existence of walks in graphs, or rather the existence of desired walks in graph. The question is, can we always construct any graph of a desired manner? But before we actually get to answering this question, let's try to formally define what a walk is. So first, we'll start with undirected networks. So what is a walk in a graph, in an undirected graph? It is simply a sequence of vertices and edges, starting and ending always at vertices, such that there are outer vertices which are nothing but the start and end vertices, and there are inner vertices which simply refer to the rest of the intermediate vertices. And there's at least one edge which connects any of the 2 vertices in a walk. So let's see an example. This is the graph, suppose, that's given to us. Then let's construct a walk shown here, as shown here. So let us trace it on the graph. So we start at node 4, then E4, go up to 4, then E5, then E6, E7 and back to 4. So this is the walk that is given to us. Now walks can be categorized into several kinds. So the first one that we will talk about is a trail. What is a trail? A trail is a special kind of a walk which does not have any repeated edges. Yet another kind of a walk is a path. A path is a walk which does not have any repeated vertices, of course with the possible exception of the first and last vertex, which may be the same. So now let us see examples of trails and paths. Let's take the same graph which we took before, and let us try to see these 3 walks and categorize which of them are actually trails and which of them are paths, or both, or even neither. So let's start with the first case. So again we start with 3. Let me trace it here. Back to 3. If you look at this walk, we see that the edge E4 is actually repeated here. We see that the vertex 4, the vertex 3, both of them are also repeated, meaning this is neither a trail nor a path. Let's look at the second walk that's given to us. Let me use a different color here. So let's try to trace it out. So what do we see here? None of the edges in this walk are actually repeated, meaning this is a trail. Is this a path? The answer is no, because if you look closely, the vertex 4 is repeated, meaning while it is a trail, it is not a path. Let's look at the third walk. Now, if you look at this walk, again, let's check for any repeated edges, and we see that none of the edges are repeated and none of the vertices are also repeated in this walk, meaning that this particular walk is both a trail and a path. Okay, before we move on to more graph theoretic definitions about walks and cycles, let me pose a question to the students. Can we say that whenever we construct a path in a graph, it is always a trail, or if not, under what conditions does it become a trail? So please try to answer this question. It's not very difficult. You can construct small examples to see it. Let's now talk about connectivity within graphs using the notion of walks. So connectivity in graphs is a very important property, because if you look at any example, for example, the case of bridges of Königsberg. Now, in that network, what we were trying to do is we were trying to move from one vertex to another through the edges in the network, constructing walks. And we were trying to comment if we can reach from one place to another, or even if we can reach starting from any place to any other place, which is precisely the notion of connectivity. Meaning, a graph is said to be connected if there exists a path between every pair of vertices. For example, let's take this graph here. If I start with at V1, I can reach all of the 3 vertices, and this holds true for every vertex, meaning this graph is connected. I can start from anywhere and reach any other vertex. Similar to this is the notion of a disconnected graph. As the name suggests, there does not exist a walk from at least one vertex to another vertex in the graph. So let's see an example of a disconnected graph. Now, a disconnected graph can look like this. So we have no edges which connect V1 and V2 to V4 and V3. Now, in the case of undirected graphs, discomponent graphs are actually generally constructed of multiple connected components. Each of these is known as a connected component. So, where do such graphs appear in real life? Now, there are several data which suggest the existence of such structures within social networks. It is very much possible for a person to be completely disconnected from others in a large network, meaning that while the others can have strong ties with each other and less number of ties with some other subcomponent, but there could still exist always a person which is completely disconnected from the rest, leading to the formation of a disconnected graph. Now, let us look at yet another notion of a special kind of a walk, which is known as a cycle. So, what is a cycle? A cycle is simply a closed walk such that the starting and ending vertices are the same. Please note this important point that In a cycle, there are always at least 3 nodes. So this property holds especially in the case of undirected networks and changes slightly when we move to the directed part. So, of course, there can exist graphs which do not have any cycles within them. We call such graphs acyclic graphs. So, let us now see some examples of a cycle within graphs. So, here is the same example. So, I request the students to pause the video here and try to see if they can calculate all of the cycles in the graph. The idea is to simply construct closed walks. So, it is very easy to see here that there are walks like this which become cycles. Now, there is a notion of a simple cycle which does not have any vertices repeated in it. Okay. So, it is the same example which we just discussed. So, let us look at yet another figure here. So, as we can see, this undirected graph does not have any cycles. Such a graph, so here there are no cycles, and such a graph is known as an acyclic graph. Okay. Now, acyclicity in networks can lead to very interesting graph structures in the case of undirected graphs. So, what are they? The first one is the notion of a tree. What is a tree? A tree is simply a connected acyclic graph, such that when we connect any two vertices in a tree, they can only be connected by exactly one path. Let us see some examples now. So again, please try to figure it out first by yourself whether this graph here forms a tree or not. So the answer to this is no, it doesn't. For example, if you try to go from vertex 2 to vertex 6, we see that there are two possible walks or two possible paths, meaning this is not a tree. What about this case? Now, we see that to every node, there always exists just one path connecting any two vertices, meaning this is a tree. Having defined a tree, let's try to see what is now a forest in a graph. Now, a forest in terms of connectivity is a slightly weaker version of a tree, in the sense that in the tree, we always had exactly one path which connected every two vertices. Here we say that every two vertices are connected by at most one path, meaning it can be either one path or even zero. So what will be the consequences on the structure of the graph? It now can make the forest disconnected, meaning unlike a tree, which is obviously always connected, a forest can now become disconnected. However, each disconnected component always forms a tree. In other words, we say that a forest simply comprises of trees. It is simply a union of trees. So again, let's see an example. So here is an example of a forest. If we see here, if we take any two nodes, we see that there is at most one path, meaning if I now take the nodes 5 and 7, we see that there does not exist a path connecting them. So between every pair of vertices, there is either one path or no path at all. So, forest comprises of multiple disconnected components, each component now being a tree. So, this is how, using the property of walks, we can create different kinds of graph structures. Now, how many of these properties carry over to the directed counterparts? So, let us start discussing about directed graphs, also known as tie graphs. So, how would we define a walk in a directed graph or a directed walk? Now, it is again a sequence of vertices starting and ending at vertices. Sorry, I'll say it again. Just make a note of this time. A directed walk is a sequence of vertices and edges which start and end at vertices, such that there is at least one directed edge between any two vertices. So, the only difference here from a walk and an undirected graph is the existence of a directed edge. Similarly, what is a directed cycle? Now, a directed cycle is a directed walk that starts and ends at the same vertex. There are some interesting aspects in a directed cycle which is different from the undirected counterpart. Now, just to remind you, in an undirected graph, a cycle needed to have at least 3 edges. However, in a directed cycle, in a directed graph, cycles can actually have a length of 1, and such cycles, which is the smallest possible cycle, is known as a self-loop. Let us now see some examples of directed walks and cycles. Okay, so let us consider this graph here and try to construct a directed walk. So, we can construct a very simple walk which looks like this. Which is this. Now, let us try to construct a directed cycle. So, which is very apparent from the figure is simply this. Meaning, E6 and back to 7. So, as you can see, the start and end vertices are the same, the starting and ending vertices. Now, as we discussed, a digraph can actually have cycles of length 1, which will look like this. This is known as a self-loop. So, we say it this way, that 5 has a self-loop associated with it. So, how can directed walks be used to comment on the connectivity in digraphs? So, this is how it goes. A digraph is said to be strongly connected if there exists a directed path between every pair of vertices, much like the undirected case. Now, instead of a digraph is said to be weakly connected if its underlying undirected graph. Now, a digraph is said to be weakly connected if the underlying undirected graph associated with the same digraph is connected. So, again, let us see some examples. The graph which is given here, as we can see, we can start from anywhere and reach every other vertex. So, meaning this graph is actually strongly connected. What about this case? So, if I am at the vertex V2, I see that I cannot move to any other vertex from here, meaning this graph is not strongly connected. However, if I now try to draw the undirected counterpart, meaning I simply let go of the orientation of the edges, then it looks like this. we can see here that we can start from anywhere and reach every other vertex in the graph, meaning the undirected counterpart is actually connected. Hence, such a graph is known as a weakly connected graph. So, this brings us to an end to the discussion on connectivity using the notion of graphs. The notion of walks, cycles and trees actually lead to the respective vertices in a graph sometimes getting very interesting properties. Some of them could act like sources and sinks, and some of them could act like globally reachable nodes. Now, such kind of nodes can play key roles in deciding the outcomes of distributed algorithms. So, we will talk more about what exactly are these nodes and how do we define them using again the notion of walks. Okay. Thank you.